screen visible?
Yes, ma'am.
Okay, so in the last class we have discussed the Rolle's law. Okay, तो आपको समझ आया Rolle's law? Is there any doubt in that? We have
No.
discussed the derivation, how this formula came, right? So is there any doubt? Everything is clear, Jibita?
Yes, ma'am.
Okay. So the conclusion was that, right? The conclusion, there are three conclusions which can be drawn from this equation, right? This equation, P total is equals to P naught A is plus P naught B minus P naught A into XP. Yeah, and you know very well what are these terms. P naught A is the vapor pressure of the pure component A, right? And P naught B is the vapor pressure of the pure component B, right? And XB is your mole fraction of B. So the conclusion was that total vapor pressure over the solution can be related to the mole fraction of any one component, right? So any one component की relate करेगा, right? The total vapor pressure. And the total vapor pressure over the solution, it varies linearly with the mole fraction, right? It varies linearly with the mole fraction. When we draw the graph between the total vapor pressure and the mole fraction, you will get a linear graph, right? You will get a straight line graph. Okay, I will show you the diagram of this, how we can just draw the graph, right, using that equation. Third conclusion was that depending on the vapor pressures of the pure component A and B, right, total vapor pressure over the solution decreases or increases, right? So it depends on the vapor pressure of pure component, which is A and B. The total pressure, it can decrease or increase with the increase or decrease in the mole fraction of component A. Okay, so see over here, this is the vapor pressure versus your mole fraction graph. Okay, vapor pressure versus mole fraction graph. So on the y-axis, we just take the vapor pressure, right? यहाँ पे हमने क्या लिया? Vapor pressure, and on the x-axis, we just take the mole fraction. Okay, so that when we plot the graph between the vapor pressure and the mole fraction, so it will give you this type of. Okay, and this vapor pressure diagram is for real or is for ideal solution, right? I will discuss what is ideal and non-ideal solution later after this, right? First, see the diagram, see the graph. So see over here, this P naught, these two dotted lines you can see over here, these are dashed line, right? This, for example, this is first and this is second dashed line, okay? So these two, you can see here, these two, it shows the PA, right? Vapor pressure of A component and your B component. This dash line, it shows the vapor pressure of A component, and the second line, it shows the vapor pressure of B component, right? It just dash line से हम show करते हैं, right? And this, you can see this solid line, right? This solid line is the vapor pressure of the total vapor pressure, right? Total vapor pressure means the vapor pressure of A component plus your vapor pressure of B component, right? So this dash and this type of graph is shown by ideal solution, right? This is the Rolle's law diagram. Okay, ये है Rolle's law diagram. ये Rolle's law diagram कहाँ से मिला है? So you just draw it using this equation. P total is equals to P naught A plus P naught B minus P naught A into XP. Okay, so when you plot the graph between the vapor pressure of solution versus your mole fraction, so you will get this type of. Okay, Jovita. So just remember this graph. Okay, this graph is very important. Remember this one. And when the solution follow Rolle's law, it is known as ideal solution, right? What is ideal solution? When the solution follow the Rolle's law. Means this graph, just a second. Yeah. Means this graph and that equation which we have derived earlier, right? अगर ये कोई भी solution अगर ये graph follow करेगा and that equation follow करेगा, it means that solution is your ideal solution. Okay? Clear, Jyobita?
Yes, ma'am.
Okay. Okay, so this graph is very, very important. Now see, if suppose Ya and Yb are the mole fraction of suppose component A and component B. Okay, अगर Ya and Yb they are the mole fraction of component A and B respectively, right, in a vapor phase. Then using Dalton's law of partial pressure, we know that what is P total? So P total, according to Dalton's law, P total is equals to your partial pressure of A just divided by your mole fraction, right? So from the Dalton's partial law of partial pressure, you can say that the vapor pressure of A component is equals to the mole fraction. What is Ya? So Ya, suppose Ya and Yb are the mole fractions of component A and component B. Okay. So Pa will be equals to Ya into mole fraction of A into your P total. Okay, total vapor pressure. Okay. So whenever in the numerical part, when the total vapor pressure is given, right, and the mole fraction is given, so you can calculate the vapor pressure of that component using this formula. Okay. Similarly, when the PB, what is PB? So vapor pressure of B component is equals to the mole fraction of B into P total. Okay. So using these equations, you can calculate your P total either, or you can also calculate the okay, vapor pressure of A component. Okay, now here's a special case of Henry's law. Okay, Raoult's law as a special case of Henry's law. So in when we talk about the gas and liquid type of solution, right? When the gas in liquid type of solution means when the solute is gas and the solvent is liquid. Okay, so that type of in solution of gas in liquid type of solution, right? Raoult's law it becomes a special case of Henry's law, right? Why it's become a special case? Because KH, Henry's constant, it becomes equal to the प्योर component. प्योर component के जो वेपर प्रेशर होता है उसके इक्वल हो जाता है, right? So that's the special case of Raoult's law, special case of Henry's law as a Raoult's law. Okay, so KH it becomes equals to the P naught, P naught of any component, whether it's P naught A or P naught B. And what is P naught A and P naught B? You know very well. It's a vapor pressure of pure component. Okay, so when the KH it becomes equal to the vapor pressure of pure component of A component or either B component, then it is a special case of Raoult's law. So then Raoult's law is becomes a special case of Henry's law. Okay, clear, Jubita?
Yes, ma'am.
Okay. Okay, so that's all about the Raoult's law. So just okay from here, in the last class you have written this conclusion part. Have you written this?
Yes, ma'am.
Okay, so from here just draw the diagram and just write down. Okay, write down, then we will do one numerical based on this.
Done, ma'am.
The question, if vapor pressure of pure liquid A is 100 mm of Hg and vapor pressure of pure liquid B is 150 mm Hg, right? And 2 mole of liquid A and 3 mole of liquid B are mixed together, are mixed together to form an ideal solution. An ideal solution. Okay, now the question is calculate the vapor pressure of the solution. Vapor pressure of the solution. Okay. So what is the question? So the question is if vapor pressure of pure liquid A is this, right? So let's write what is given first. Okay. So pure liquid it is given, right? So means P naught A is given, which is 100 mm Hg, right? And the vapor pressure of pure liquid B means P naught B is 150 mm Hg. Okay. Now the number of moles is also given. Number of moles of A liquid is 2 mole and the number of moles of B liquid is 3 mole. Okay, and they are mixed together to form an ideal solution. And we have to calculate the vapor pressure of liquid. Okay, so first we just have to calculate what is vapor pressure, total vapor pressure of solution we have to find, right? So we know that by Raoult's law, what is the formula? By using Raoult's law, what is the formula? P total means P of solution, vapor pressure of solution is equals to your PA plus PB, right? And PA plus PB, you can write PA plus PB means vapor pressure of A plus vapor pressure of B. And we know that vapor pressure of A is equals to P naught A into P naught B, sorry. Just a second. It's P naught A. P naught A into XA plus P naught B into XB, right? Means the vapor pressure of pure component A into its mole fraction, right? And plus the vapor pressure of pure component B into its mole fraction. Now for this, we should know what is the mole fraction here, right? Mole fraction, we have to calculate it, right? Because P naught A value and P naught B value is given and the number of moles is given. So how to calculate the mole fraction? Okay, so mole fraction of A is equals to number of moles of A upon the number of moles of A plus number of moles of. Okay, that's the formula of mole fraction, right? So now just calculate it. Number of moles of A is given 2 upon the number of A, moles of A, which is 2 plus 3, means 2 upon 5. Right? The mole fraction of this A is 2 upon 5. Okay, means your 0.4. 0.4. Now, similarly, just calculate the mole fraction of B, Jovita. Just calculate the mole fraction of B and just tell me the answer. Done?
No, ma'am, doing it.
Okay, just do it.
Four,
Four.
four. Total
Mole fraction. Just tell me the mole fraction of B. You know
okay.
the formula? You know the formula. What is the mole fraction? How to calculate? Just tell me the formula first. What is the formula for the mole fraction?
Total number of moles of B divided by total number of moles in liquid
Number
B.
of, yeah. So it's number of moles of B, right? B formed
0.5.
divided by, yeah, 0.6.
5.
No, it's not
6.
5. Okay, so total number of moles is 2 plus 3, right? Okay, you can just first write down the formula. So it will be the number of moles of B is 3, right? 3
Yeah.
upon 2 plus 3. So 3 upon 5. So it will give you 0.65. 5 6 are 30, right? So 0.6, not 0.5. Okay. So now we have just calculated the number of moles of mole fraction of A and B. Now substitute the value here and you will get the answer. P naught A value is given, which is 100 mmHg into XA value. Mole fraction of A is 0.4, right? Plus it's given 150 into mole fraction of B is 0.6. Now solve it and tell me the answer. It's 40. 40 plus 90. 40 plus 90. So it will give you 130 mm of Hg, right? So what is the vapor pressure of the solution? So vapor pressure of the solution is 130 mm of H. Got it?
Yes, sir.
Just write down the solution. Okay. Okay, so the next topic is, Jovita, it's ideal and non-ideal solution. Okay, so let's see what is ideal and non-ideal solution. So ideal solution are basically the solution that follows Rawls law, right? Over the entire range of concentration. Concentration kuch bhi ho, so it will follow the Rawls law. Okay, so just write it down. What is ideal solution? So it obey Rawls law over the entire range of concentration. Concentration. Right? And what are non-ideal solutions? So non-ideal solution did not obey the Rawls law, okay, over the entire range of concentration. Means ideal solution will not follow that graph, okay, and will not follow that equation which we have derived. Okay, P total is equals to P naught A, that type of that equation. Okay, so those solution which doesn't follow the obey or obey the Rawls law graph. Okay, so that are known as non-ideal solution that did not follow, right? But those solution which follow that Rawls law graph and Rawls law equation, that is known as ideal solution. Okay, do not obey Rawls law over the entire range of concentration. Right, and just remember that ideal solution. So liquids with similar intermolecular force of attraction, it forms ideal solution. Okay, ideal solutions कौन बनाते हैं? The liquids which have similar intermolecular force of attraction, right? मीन्स द पोलर वन, जो पोलर होंगे वो बनाएंगे आइडियल सॉल्यूशन, नॉन पोलर एंड नॉन पोलर वन दे विल मेक द आइडियल सॉल्यूशन. Okay, so you can just add it at the point. It's important. Liquids, liquids with, or you can just write down the note. Notes में आप बना के लिख सकते हो. Just okay. I'm writing it here. No, right. Liquids with similar intermolecular force, intermolecular force of attraction forms ideal solution. Okay, ideal solution. For example, just like benzene, right? Benzene and toluene, benzene and toluene, your N-hexane, N-hexane and N-heptane, right? N-heptane, right? So you can see over here, or both are non-polar. Benzene is also non-polar, toluene is also non-polar, N-hexane is also non-polar, and N-heptane is also non-polar, right? So the liquids which have similar intermolecular force of attraction means you can see over here benzene and toluene, they have similar intermolecular force of attraction, so they are forming ideal one, ideal solution, right? When you add benzene to toluene, you will get an ideal solution which obeys the rules. Okay, and when you add N-hexane and N-heptane, you will also get a ideal solution. Why? Because their intermolecular force of attraction are similar, right? Because both are non-polar type. Both are non-polar. If you add one polar and non-polar, then you will not get a ideal solution. Okay, just remember that. Like अगर आप polar ले लोगे कोई भी, for example acetone and benzene, when you add this, so you will not get a ideal solution. Okay, so for the ideal solution, liquids with similar intermolecular force of attraction, they forms the ideal solution. Just remember that. And another examples you can write, like if I give you polar example, so chloroethane and and bromoethane, right? They will form the ideal one. Both are polar in nature, right? So they will form the ideal one. Why? Because their intermolecular force of attraction are same. Okay, are anyhow similar. That's why they are forming. When you add these two, you will get a ideal solution. Clear, Jyobita? Got it?
Yes, ma'am.
Okay. Now see, so ideal solution are those which obeys the Raoult's law, right? And non-ideal is those which did not obey the Raoult's law. Okay. Now see, the enthalpy change of mixture, right? When you add two components together, so when the enthalpy change, right? So enthalpy change of mixture is always equals to 0 in the case of ideal solution, right? अगर आपका ideal solution बन रहा है, for example, if you add benzene and toluene, right? So you will get when you add these mixtures, right? जब उन दोनों को आप add करोगे, जो mixture बनेगा, तो उसका जो enthalpy change होगा mixture का, that is always equals to 0, right? In the case of ideal solution. Okay, so ideal solution के case में delta H mixture is equals to 0. Okay, so it's the enthalpy change. And volume change of mixture is always equals to 0, right? Volume change of mixture is 0 in the case of ideal solution. Clear? But in the non-ideal solution, right, if the solution is non-ideal, then enthalpy change is not equals to 0. It can either be positive or negative, right? I will discuss when it will be positive and when it will be negative. There are two cases, right? Two deviation it will show. Non-ideal solution के case में there is two deviation, right? So in the non-ideal solution, delta enthalpy change of mixture is not equals to 0, and the volume change of mixture is also not equals to 0. Clear? Now see, yeah, see the AA and interaction means between For example, there are two components, A components and B components, right? So the A interaction means the components A और components A के बीच में जो interaction होगा, उनके molecules के बीच में जो interaction होगा, and the B interactions, they are equal, right? They are equal to AB interactions, right? A is what? A is first component, A component, and B is second component. When they interact with each other, जब दोनों mix होंगे, so there will be a solution. They form a solution which is AB solution, right? So AA interaction and BB interactions are equal to AB interaction, right? AB interaction, see, AA and BB interaction जो होगा, these are equal to AB interaction. Mixture का जो interaction होगा, when they form the mixture, then the molecules of A and B का जो interaction होगा, it will be always equals to AA interaction and BB interaction. In the case of ideal solution, right? In the case of ideal solution. Now, see first the ideal one, let's complete it. Examples are solution of N-hexane and N-heptane, okay, as we have discussed, bromoethane and chloroethane and benzene and toluene. Okay, these are some examples of ideal solution you should learn, right? You should know about it. Just remember these examples. N-hexane and N-heptane, right? Both are non-polar, right? Bromoethane and chloroethane, and both are polar one, and benzene and toluene both are non-polar, so they also give the ideal solution. Okay, now let's see what is non-ideal. So non-ideal, we know that they don't follow the Raoult's law. Okay, and the enthalpy change of mixture is not equals to zero. It can be positive, negative, and positive होगा. ये zero के equal नहीं हो. Okay, and the volume change of mixture is also not equals to zero. Right, volume change भी positive होगा either, or it can be negative. Positive or negative. Okay, now let's see. In the okay, so the non-ideal के case में there are two deviations, right? They show either negative deviation or positive deviations from the Raoult's law. Okay, because we know that non-ideal solutions don't obey the Raoult's law and their graphs, right? So there are two types of deviation which is shown by non-ideal solution: negative deviation and positive deviation. Right, now let's see what is negative deviation and what is positive deviation. Okay, so see what is negative deviation and what is positive deviation. So in the negative deviation, right, when we talk about the negative deviation, so you can see over the first, see the graph. See the graph. Ideal के case में क्या graph था? Just a second. Yeah. Okay, that was the graph which was the ideal solution graph, right? Right, which obeys the Raoult's law. So ideal solution के case में just a similar ये graph होगा. Okay, but for the non-ideal solution, it doesn't follow the Raoult's. Right, see the graph, these two graphs. This first graph is the negative deviation. Negative deviation. Why it is negative deviation? To see, again, this is a vapor pressure versus mole fraction graph, right? Vapor pressure, we just take it on the y axis, right? And mole fraction, we just take on the x axis, right? Similar graph hota hai, but here, this is the ideal, jo green, see, you can see which, the line which is drawn by blue, right? This is the ideal graph. ये जो blue से जो line draw है, this is your ideal graph, ideal gas equation, ideal solution graph, not ideal gas, ideal solution graph. And this red, right? So in the negative deviation, this ideal, because we know that non-ideal solution doesn't follow the Raoult's law and its graph, तो उसकी तरफ तो graph होगा नहीं. But this shows this negative deviation में क्या होता है, ये जो P total, this is P total, right? This line was P total, this was PB, right? Partial vapor pressure of B component, and this line was partial pressure of first component, A component, right? ये line था, but in the negative deviation, what happens? This graph just like ये इसकी below जाता है, right? ये जो P total का जो graph है, इससे नीचे से ये line cross होती है, P total K line, right? Similarly, in the case of PB, right, second component, so here this line shows the deviation, the negative means नीचे से जा रहा है line. ये जो line है, This goes just like this. Okay, this red line. This red line shows the negative deviation, right? Negative deviation. Okay, so its P total, it decreases, right? The vapor pressure of components also decreases, and the P total pressure, vapor pressure of total vapor pressure also decreases. Okay, and it doesn't follow the Rolle's law, and it gives the negative deviation. Negative deviation के केस में ये यहाँ पे ये वाला ये this line, red line, जो this shows the negative deviation. Okay, and this blue line, it shows the ideal gas. जो ideal के केस में था जो graph, this line shows the P total of the ideal gas, but it doesn't follow the ideal gas graph and Rolle's law graph, so it gives a negative. यहाँ से ये pass होती है. Similar case, in the case of positive deviation, this second graph, it shows the positive deviation. Positive deviation का ये graph है, right? Again, it's a vapor pressure versus mole fraction graph, right? But in this case, this is positive. Positive ka meaning, okay, the positive direction is, so here you can see over here this dotted line, the dotted red line, it shows the positive deviation, right? This blue line, it shows the P total in the case of ideal solution, right? Ideal solution का जो Rolle's law graph था, you can see over here, right? This was the graph, P total. But in the case of positive and negative deviation, this line just in the case of positive deviation, this line it goes top, right? This P total line ये ऐसी होती है. Similarly, PB के केस में this line goes like that. इसके ऊपर से this line इस line के ऊपर से जाती है. Similarly, just like this. This is the positive deviation. Similarly, अगर negative deviation होगा तो this line it goes below, right? Below from this line. Okay. So that's the positive and negative deviation, which is non-ideal gas equation. So non-ideal gas equation, it shows positive deviation and negative deviation. Okay, so let's see, because we know that no, in the case of non-ideal solution, the enthalpy change of mixture is not equals to zero. It can either negative or positive, right? So let's see when it is positive and when it is negative. So let's see. So in the case of negative deviation, if the solution is negative deviation, right? If the solution, it follows the negative deviation, so its enthalpy change is always less than zero. Okay, so if it is less than zero, it means it is negative, right? And again, the volume of mixture, right? Volume change of mixture, again, it is less than zero, right? Means the volume is also negative. Volume of mixture is negative, right? In the negative deviation. Negative deviation के case में क्या है? Delta H is also negative and delta V of mixture is also negative. Okay? Clear जो भी तो समझ आ रहा है?
Yes, ma'am.
Okay. See the positive deviation. Similarly, positive deviation के case में the enthalpy change of mixture is greater than zero, right? If it is greater than zero means it's positive, right? And if delta V of mixture means the volume change of mixture is also greater than zero, means it is also positive. It's also positive. Okay. So that's all about the ideal and non-ideal gas, ideal and non-ideal solution. Now see, let's talk about the interactions. Okay, so AB, in the case of negative deviation, A and B components के बीच में जो interactions होते हैं, they are stronger than those of AA and BB. Okay, in the case of negative deviation, A and B components के बीच में means जो solution जब बन जाता है, जब mixture आपका बन जाता है, after adding the solute and solvent components, right? After adding the components, when the solution is prepared, then the molecules के बीच में जो interaction होता है, A component and B component के बीच के molecules के बीच में जो interactions होते हैं, they are stronger than those of AA and BB components. Okay, and the example is a mixture of HCl and water, right? HCl and water का जो mixture होता है, that is example of negative deviation. That is example of non-ideal type of solution. And non-ideal में किसका type होता है? So it's a negative deviation. Okay, mixture of acetone and chloroform CHCl3. It's again an example of negative deviation. Okay. Now let's see what are the positive deviation. So in the positive deviation, AB interactions are weaker. AB interactions जो होते हैं, they are weaker than those of AA and BB interaction. And the example is mixture of ethanol and water. Ethanol and water का जो mixture होता है, that is its example of positive deviation. It follows a positive deviation. Okay, when you plot the graph of the mixture of ethanol and water, when you mix these components, so you will get this type of graph. आप वेपर प्रेशर और मोल फ्रैक्शन का ग्राफ जब प्लॉट करोगे तो यू विल गेट all this type of graph in the case of mixture of ethanol and water because it follows the positive deviation rule. Okay, similarly it's acetone and ethanol. When acetone and ethanol, when you mix it, you will get a non-ideal solution. And which type of non-ideal solution? So it's a positive deviation. It follows positive deviation. Okay, positive deviation means the enthalpy change of mixture is positive, right? And the volume change of mixture is also positive. Okay, so you just have to remember this. Sometimes in the question they uh, um, ask you the difference between, write down the difference between or differentiate between the ideal solution and non-ideal solution. Direct question aata hai isse. Okay, so just remember this. It's very important. Okay, Jibita, is it clear?
Yes, ma'am.
Okay, so please just write it down. Write down the difference. Then can I scroll down? Written, Jyobita?
Yes, ma'am.
Okay, so see, the next topic is, let's see, what do we mean by azeotropes? Azeotropes. Do you know what is azeotropes? Hmm?
Yes.
Okay, so what are azeotropes? Tell me.
I forgot.
Forget?
Yeah.
Okay, see, there is a mixture which is known as azeotropic mixture, right? So when the solutions of completely miscible liquids, right? When the solution is completely miscible, right? So it boils at a constant temperature, right? And it can be distilled over without any change in composition, right? Without any change in composition, they are known as isotopic mixture. तो क्या होता है isotopic mixture? So it is a solution of completely miscible liquids, right? When the two liquids, when they combined, so they when they are completely miscible, वो पूरी तरह से mix हो जाते हैं, right? So उनकी जो boiling point होती है, right? So boiling point, they boils at constant temperature, right? So the completely miscible liquids, they boils at constant temperature and they can distill over without any change in composition. आप उसे डिस्टिल कर सकते हो, डिस्टिलेशन कर सकते हो उसका और उसे अलग अलग कर सकते हो डिस्टिलेशन करके, राइट? सो दे आर नोन एज एजियोट्रोपिक मिक्सचर. Okay, and there are two types of azeotropic mixture. First, write down the what is azeotropes or azeotropic mixture. So the solution, you can write azeotropes. Azeotropes, they are the solutions which boil at constant temperature. Okay, in simple words, you can write azeotropes are the solution which boil at constant temperature. Okay, and azeotropes they have same composition, same composition in in liquid and vapor phase. Right, in vapor phase and in liquid, they have same composition. Composition doesn't change, means constant composition, okay, right? And the components means the liquids, the miscible liquids, you can just separate, yeah, composition components, or just simply write, okay, simply write that there are two types of azeotropic solution. Types, you can write types of azeotropes, right? Two types. के होते हैं azeotropes. First one is your maximum boiling azeotropes, maximum boiling azeotropes, and the second one is your minimum boiling azeotropes, minimum boiling azeotropes, maximum and minimum boiling. Now let's see what are maximum boiling azeotropes and minimum boiling azeotropes. So the solution which shows large negative deviation, right? That type of solution which shows a large negative deviation from the Raoult's law, right? Raoult's law से negative deviations show करेगा, that is your maximum boiling azeotropes. Okay, so just write down the solutions which shows large negative deviation, large negative deviation from Raoult's law, from Raoult's law, right? They form maximum boiling azeotrope, right? Azeotropes, right? And what is minimum boiling azeotropes? So the solution which shows large deviations, large positive deviation, right? That's minimum. Okay. So you can write the solutions which shows large positive deviation, positive deviation from from Rolle's law. They form they form minimum boiling azeotropes. Minimum boiling azeotropes. Okay, and the example is just similar to the your negative deviation example and positive deviation example. Okay, yeah. Means these solution HCl and water solution, these will these will form the maximum boiling azeotropes, right? Because they show the large deviation, negative deviation from Rod's law, right? And your mixture of ethanol and water or acetone and ethanol का जो mixture होंगे, they will show or they will form the minimum boiling azeotropes, right? Because they show the large deviation, large positive deviation from Rod's. Okay, so that's all about the azeotropes and azeotropic mixtures. And yeah, just write one more point you can just write because you can see over here the azeotropes are solution which boil at constant temperature, right? Means the solutions के जो temperature constant होते हैं तो so you can't the azeotropes or the components of azeotropic mixtures, right? The components of azeotropes cannot be separated by fractional distillation. Just write it down. You can't separate components of azeotropes cannot be separated by fractional distillation. Fractional distillation, right? Because you can see over here, they have constant temperature. They boil at constant temperature. Okay, so that's why you can't separate both the components by fractional distillation. Okay, got it, Jovita?
Yes, ma'am.
Okay, so please just write it down. Done, Jovita?
Yes, ma'am.
Okay, so that's all for today. I think the time is up. Okay, in the next class, we will start with the colligative properties. And the colligative property is very, very important. Okay, so we will discuss in details and we will do the questions along with that. Okay,
Okay,
Vachu?
ma'am.
Okay, so if there is any doubt, so you can ask. Everything is clear?
Yes, ma'am.